Okay, last part, talking about graphing. So, we're on page 4 of our guided notes, Unit 1. Now, when it comes to graphing, the first important thing is to recognize what variables you have, which one's the independent and which one's the dependent. Okay, so a variable is anything that's going to affect the outcome, or it's kind of like a recognition of that outcome. The independent variable is the factor that the scientist or whoever's doing the experiment is changing. And then the dependent variable is what occurs because of that change. So like in this situation, we have springs, we have mass hanging on a spring, and then we have the length of the spring as it's being pulled, okay? And so the factor that the experimenter is controlling is how much weight they're putting on that spring. And then, depending on that weight, the length will change. So the dependent variable depends on what's happening with the independent variable. Okay? Now, traditionally, we put the independent in the y-axis, and we put the dependent in the x-axis. Okay? So now, we know, and so we need to identify our dependent and our independent. So the independent was the mass, and the dependent was the length of the spring based on that mass. And I want you to construct a graph from these values. Don't forget to label your axes, as well as telling me what units you're using. So hit pause, label and create your graph, and then compare it to what I have here. Okay, so go ahead and do that. All right, so what we see when we graph these values, it appears that we have a linear relationship. That best fit line, that line that fits the best amongst all of our data points, is essentially a straight line. And so we would call this a linear relationship. Okay, so in a linear relationship, that value can be expressed as y equals mx plus b. And the slope, as I'm sure you've heard in math, your slope is rise over run. And that can have really important meaning if we look at those two values. So in the y-axis, we have distance, and in the x-axis, we have time. So rise would be distance in miles, and run would be hours. So when we look at that slope, we're looking at miles per hour. And I'm sure you recognize that. I'm sure you recognize that as speed, your miles per hour. And so that's what this represents. For this particular graph, the slope of this line is the speed of the object. So now let's write, knowing this, let's write an equation for distance. Okay, so here we have distance over time, and we know that equals the speed. Okay, so let's give those some variables that we can work with. We're going to call speed velocity, v, and that's going to equal our distance. So I've seen that expressed as a d or an x over a time value. And now we're going to solve for distance. So times both sides of the equation by time, and we have distance is equal to velocity times by time. Okay, so that's our first kind of graphical relationship that we're looking at. Here's the second type. nonlinear relationships. Okay, so in a nonlinear relationship, like you can see, there's some kind of relationship that the line isn't straight. Usually we see curves like this. For our nonlinear relationship here, it's a quadratic, and that's the line that best fits there. Okay, now we're going to get into this in more detail later, but the big thing I want you to know that you may want to add to your notes, that some of these nonlinear relationships are proportional and other ones are inversely proportional. Okay, so when something is proportional, when two variables are proportional, if one goes up, then the other one goes up, or if one goes down, then the other one goes down. But if they're inversely proportional, then the opposite happens. If one goes up, the other one goes down. Okay, so let's look at this. We have the variable of position, and we have the variable of time. And as time gets bigger, the position is getting bigger. And so they're proportional, because as one of the variables goes up, the other one goes up. Or if we went the other direction and we made time smaller, well, the position got smaller as well. So when one went down, the other one went down. Okay, so that's a proportional relationship. Okay, so what I want you to do is an example problem. I want you to try this one at home by yourself. So look at this, determine what the independent and the dependent variables are, place them on the correct axes, go through and find all your data points, recognize if it's linear or nonlinear, and then ask yourself if it's proportional or inversely proportional. When I look at this graph, it's nonlinear, but it's an inversely proportional relationship. How do I know this? Okay, we have our two variables. In this case, we have ohms, and then we have current. Okay, we worked with that equation, right? V equals IR. So when I look at this, I realize as my current is getting smaller, okay, so as this is getting smaller, my resistance is getting larger. Okay, so as one went down, the other one went up. Or if I go this direction, I look at this one, I say, okay, if I want to have less resistance, well, as I go into less resistance, I'm getting more current. And so they're inversely related to one another. They have an inversely proportional relationship. All right, so that's the big idea with graphing. We have three relationships. We have linear, then we have two nonlinears. The first nonlinear was a proportional relationship, and the second nonlinear was an inversely proportional relationship. We talked about direct or proportional versus inversely proportional. We looked at some examples of that. And then you can use these graphs to make predictions. Like, you could look at this graph, and I could ask you, if I increase my resistance, what's going to happen to my current? Okay. All right, guys. Got through the first day of notes. Good job. If you have any questions at all, feel free to email me, and I'll get back to you within 24 hours. And don't forget that you can always check in during office hours through our Google meeting to ask me any questions that you have. All right, guys. Have a wonderful day.